Good afternoon, everyone. This small rover right here is called LRRS, the Lunar Radiation Recording System, and in this video we will explain how it works and what we did to make it operational. The presentation is divided into 4 parts, explained by the 5 people on the team. First, Elisua Larraguibel will explain what the robot is and its main objective. Next, Sage Serrano and Rika Kaluvakiv will go over the code used for the radiation detector and how it outputs the data into an SD card. Then myself, Kevin Vizcarra, will explain how to interpret that data in an Excel chart. And finally, Jose Espinosa will share the challenges we faced during that project. Let's not make it longer, why don't we get started?
Good morning, everyone. Our project, LRMS, is a lunar exploration ground mission designed to use a self-driving rover to traverse the moon and record radiation levels from the sun. While it's possible for humans to return to the moon, one of the biggest challenges is the extremely high radiation exposure due to the lack of an atmosphere. The goal of the project, LRMS, is to collect radiation data at multiple points on the moon and chart those levels. This data will serve as a foundation for making future human exploration missions safer and better informed. Our rover uses a radiation sensor along with other Arduino-based components to measure and log data to an SD card for later analysis. As it travels, an ultrasonic sensor helps it detect and avoid obstacles, allowing it to navigate safely and complete its mission. From our Earth-based test runs, we recorded a baseline radiation level of about 0.1 microsieverts per hour. We expect that on the moon, readings could be up to 200 times higher. Understanding these levels will help us determine the right safety measures for future lunar missions, whether for short visits, long-term exploration, or even potential encampments.
The main component utilized in the LRRS is the Kjo version 1.1 Geiger counter, an Arduino-compatible radiation sensor including a Geiger-Mueller tube and active buzzer on board. We've connected this sensor to the Mega Elegoo 2560 and SD module in order to get readings out of the data collected. The radiation sensor starts by taking an ionizing radiation such as alpha-beta particles, gamma rays, and X-rays through the Geiger-Mueller tube. This tube is filled with low-pressure noble gas that, when mixed with the particle, causes ionization and creates positive ions and leftover electrons. This reaction within the tube creates an electric pulse that is then sent to the active buzzer, creating a prominent clicking noise to indicate a radiation read.
As the Geiger-Mueller tube detects radiation by generating a small pulse each time a particle passes through, the Arduino uses an interrupt to count these pulses during each 20-second window. This project uses an SD card module to log radiation data detected by the tube. The module connects to the Arduino Mega using serial peripheral interface with pin 53 as a chip select. The code opens a file, writes new data every 20 seconds, and closes the file to save it safely. From that, it calculates counts per minute or CPM and then converts it to microsieverts per hour using a standard conversion factor for the J3152. This radiation level gives an estimate of how much exposure a person is receiving. The data is shown in the serial monitor and stored on the SD card with a timestamp so it can be reviewed later.
Okay, so now let's move on to our data. And as Rika explained earlier, our code records the radiation levels in microsieverts, and that's really useful, but we can still do more with it. Let's go to Excel. And why? Because we can export that exact data right here from just going to the option of data tab, going to from text/CSV. Why? Because our data is on a .txt file type, and we can choose whichever we want, whichever try we want. In this case, I chose CPM LOG4. Why? Because this was a pretty interesting trial. Our robot in this case moved the whole 2 minutes and the 20 seconds in a pretty linear path, and that's going to be useful for later calculations. So let's just import this data real quick. And it's gonna give us this table right here. It looks kind of messy because the CPMs are broken down into 2 columns as well. Not only the CPMs, the timestamps are broken down as well. But that's okay. The only thing that we want on its own column is microsieverts, basically the radiation level. We're just gonna load it like that. That's perfect. Okay, and like I said, not only the CPMs are broken down in the 2 columns, they are in minutes, and since we want everything in SI units, we're just gonna put it in seconds as well. That's gonna help us for later calculations. I'm gonna explain that right now. So we're gonna start on the same row that our data started on the 20 seconds. We know that our next timestamp is gonna be 40 seconds. Is F2 plus 20. Perfect, that's 40. And the next is gonna be 60 because it's 1 minute. The next one is gonna be 1 minute and 20, which is 80 seconds. But I'm just gonna drag my mouse down and it's gonna convert all the minutes to seconds. Now I just have to copy and paste these radiation levels right here so it matches each of the data points. This is gonna be your x-axis, which is the time, and the y-axis, which is the radiation. So I just select it, insert chart, and now we have a chart that not only it looks a little bit more pretty. With this setup, the chart that we created is gonna make the variation of the radiation much easier to visualize. Even though the graph looks like there's like a big change between each point, there's really not. The difference is actually small between the maximum point and the minimum point. There's just a difference of 0.1197 microsieverts. I'm just gonna put this on data table because it's a little bit more pretty. It's the same information. So yeah, actually the y-axis are just like zoomed in. That's why it looks like there's a big change, but like I said, there's not. This output and as a graph is useful, like I said, to visualize it. But with this, we can also find, for example, the distance which each of those points were recorded. Because we have the time, we can somehow figure it out where these exact radiation points were measured. So let's do that right now.
Okay, so we can see right here that we have a measuring tape of approximately 200 centimeters. We will let our car travel that distance and record that time, which according to our stopwatch was 4.73 seconds.
So we know that the velocity is equal to the displacement over the time. As long as the velocity remains constant, of course, because if it was variable, then we'll need to consider acceleration and use calculus or kinematic equations to solve the problem. We're still going to use some calculus, but it's the easy one. We don't have to worry about it. But however, in this case, the velocity is constant, so the math is much simpler. Okay, so we know that our robot traveled 200 centimeters for about 4.73 seconds. Since we want the displacement in SI units, we simply convert centimeters to meters, and that's going to give us the robot's velocity in meters over second. So we just multiply 100 centimeters per meter, which is just going to be 2 meters over 4.73 seconds, which is equal to 0.4228833 meters over second. And yeah, this is good, this is okay, but I really don't want to be writing this big number on all my calculations, so I'm just gonna keep this number, which is exactly the same as this one. It is much simpler, 2 over 4.73 seconds, meters over second. So that's perfect. Okay, so now we just have to restate that the velocity is a change in displacement over time. More formally is saying that the derivative of x in respect to time. Here the process becomes easier because we only need to solve for x, and we'll call the x, well, we know that this is velocity, so it's 2 over 4.73 seconds. And in this case, like I said, I'm gonna call the displacement x microsieverts. And why? Because this is basically representing the location of the radiation reading that we want to analyze from our data table. This position is found by integrating the x, where the lower limit is 0, since as shown in the video we start from position 0, and the upper limit is a point where the chosen radiation reading was recorded. So let's just put everything together. 0 all the way to x microsieverts dx, and this is equal to the integral of velocity with respect to time. Again, starting from t equals to 0 and ending on the time when the desired measurement was taken. So 0 all the way to t, dt. So x microsieverts time is equal, oh sorry, you have to multiply with velocity. It's 4.73 dt. Okay, so it's equal to 2 over 4.73 times time. Okay. Okay, now we know how to find the distance with this function, but we know that at the end that's just going to be an approximation because the robot is not always going to follow a perfectly straight path. Normally due to the ultrasonic sensor, because well, the robot occasionally is going to turn right or left before returning to its original course, but that's okay. This method is still effective because radiation levels do not appear to change significantly over short distances or time intervals. They actually tend to remain constant for extended periods, and variations are more likely caused by the factors such as the altitude or precise positioning. Now let's do some examples. If I want to find the location with the highest radiation, basically the location where I don't want to go, we just look at the table, the sample table where our robot actually followed most of the time a straight path. We're gonna look for the maximum value right here. In this case, the maximum value is 0.171 microsieverts per hour, and this was recorded 80 seconds after starting the trajectory. So to know the distance where we have this radiation level, we just use our function, microsieverts 80 equal to 2 over 4.73 times 80, which is gonna be equal to 33.82 meters. But if I was an astronaut, well, yeah, it's good to know where the most radiation is, but I want to know where the less radiation is, because that's where I want to go, that's where I want to put my base, for example. So likewise, for the lowest radiation level on this table, we're just going to check the minimum value in the graph, which in this case is going to be equal to 0.0513 microsieverts per hour, and that was recorded at 100 seconds after start of the trajectory. So we just basically put everything together. 100 equal to 2 over 4.73 times 100 equals 28 meters. Okay, so that's how we find the distances. Some examples, but let's do another example before finishing this part. Let's say that I was on the moon and I actually have limited resources. I don't have that much gas on my lunar car. In this case, let's say the only distance that I can travel is 50 meters, but I want to know how much radiation I'm going to be exposed to at that distance. Well, so we can still use this formula, but using simple algebra. In this case, we're going to substitute x microsieverts by that distance, and now we can find the time. 4.73 time, we solve for the time, 15 times 4.73 over 2. That will be equal to 35.475 seconds. And if you can check the graph right here or the table, I don't have an exact value for the radiation at this time, but well, why? Because remember that our code does the CPMs between 20 seconds intervals, so it goes from 0, 20, 40, 60. So the only thing that we can do right here is basically to round this number to the closest available time, which is going to be 40 seconds. And at 40 seconds, the radiation measured was 0.0684 microsieverts per hour.
As a team, we encountered numerous challenges throughout the project. Initially, in our radiation code, we received no valid input from our sensor. Every click signal that our radiation sensor sent to our Arduino was a low signal, which we initially mistook for a high signal. Furthermore, the detector outputs were initially high, exceeding 3,000 counts per minute, whereas normal background on radiation on Earth typically ranges between 0 and 60 counts per minute. Also, we noticed another problem. The counts per minute continued to increase, adding to the previous values rather than resetting as expected. In addition, our SD card module presented its own difficulties. The radiation detector and the SD card failed to communicate between each other, and the SD card was unable to open a file for data storage. Collectively, these issues highlighted the need for extensive troubleshooting before the system could operate as intended. But through collaboration and persistence, we were able to successfully resolve these challenges as a team.